Today we're going to talk about using fundamental identities. Do you enjoy solving puzzles? I bet you do. They're a healthy and fun way to pass a Saturday night, as well as a great way to practice problem-solving skills. I bet you didn't know this, but solving puzzles actually releases pleasure chemicals in the brain. Perhaps this is why, for over 12,000 years, people have been fascinated by solving puzzles. In calculus, we're often faced with trigonometric expressions that need to be simplified. One way these complicated trigonometric expressions can be simplified is through factoring or writing the trig expression over one common denominator. I do appreciate the well-wishers out there. Many of you have asked me, how is my calf doing? And I'll let you know, she's getting bigger every day. She's eating a lot of, not rice, but rather grass. As you can see, little Bessie's getting bigger and stronger every day. Soon she's going to be producing milk. I promise her first glass of milk will be shared by all of us in this class. We know that the three basic trig functions have reciprocals. What are they? Well, sine theta has a reciprocal 1 over cosecant theta, which of course is 1 over sine theta. Keep, change, flip means 1 times sine theta over 1 gives us what we started with. Cosine theta is 1 over secant theta, which is 1 over cosine theta. Keep, change, flip gives us 1 times cosine theta over 1 gives us what we started with. And tangent's reciprocal is 1 over cotangent theta, which is 1 over tangent theta. Keep, change, flip gives us 1 times tangent theta over 1 gives us tangent theta. The main point here is the reciprocal of sine is cosecant. The reciprocal of cosine is secant. The reciprocal of tangent is cotangent. I don't think I'm telling you anything you don't already know. Well, if we know those first three reciprocals, we get these for free. The reciprocal of cosecant is 1 over sine. That's what cosecant is equal to, 1 over sine. Secant can be written as 1 over cosine. Those are reciprocals as well. And the reciprocal of cotangent, 1 over tangent theta. When we used a unit circle, of course, our radius of the circle is 1. That's what makes it a unit circle. And we're going over x and up y. And we learned that the x is cosine theta and the y is sine theta. Because if we put our eyeball at this perspective, then opposite over hypotenuse is y, which is sine theta, and adjacent over hypotenuse is x over 1, which is cosine theta. So cosine theta is the x and sine theta is the y. If we go over x and up y, we're really going over cosine theta and up sine theta, which brings us to quotient identities. Tangent theta is opposite over adjacent. Of course, that's y over x, or sine theta over cosine theta. If cotangent is adjacent over opposite, that means cotangent theta can be written as cosine theta over sine theta. We call tangent theta is sine over cosine a quotient identity, and cotangent is cosine over sine. That's also known as a quotient identity. Notice that these are still reciprocals. Sine over cosine's reciprocal is cosine over sine. If we have this unit circle here with x and y and 1 as our radius or hypotenuse, our right angle is here. We know the Pythagorean theorem is a squared plus b squared equals c squared using this triangle. Leg squared plus leg squared equals hypotenuse squared. If we apply that to this right triangle from the unit circle, we see we have our first Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. Now, in math, we don't write sine theta squared like this. We put the squared between the sine and the theta. We put the square between the cosine and the theta. I know that notation's a little different or new to you, but you read this as sine squared theta and cosine squared theta. Sine squared theta is really this. Why does this migrate here? I don't know. If we take our first Pythagorean identity, sine squared theta plus cosine squared theta equals 1, and we divide each and every term by sine squared theta, by sine squared theta, by sine squared theta, we're left with 1 plus cosine squared over sine squared is going to give us cotangent squared theta is equal to 1 over sine squared is cosecant squared theta. And here is our second Pythagorean identity. First we have sine squared theta plus cosine squared theta equals 1. And now we have 1 plus cotangent squared theta equals cosecant squared theta. And you can see where it comes from. Similarly, if I take my first Pythagorean identity and I divide each and every term by cosine squared theta, by cosine squared theta, by cosine squared theta, I wind up with tangent squared theta, that's sine over cosine, plus 1 is equal to 1 over cosine is secant, but we're squaring it now. And here is another Pythagorean identity. Tangent squared theta plus 1 equals secant squared theta. Okay, this is what we have so far. Reciprocal identities. Sine theta is 1 over cosecant theta. Cosine theta is 1 over secant theta. Tangent theta is 1 over cotangent theta. Cosecant theta is 1 over sine theta. Secant theta is 1 over cosine theta. Cotangent theta is 1 over tangent theta. Get those down in your heads. Tangent is sine over cosine. Cotangent is cosine over sine. Pythagorean identities. These are probably new to you. Sine squared theta plus cosine squared theta equals 1. 1 plus cotangent squared theta is cosecant squared theta. And tangent squared theta plus 1 is equal to secant squared theta. The quicker you know all of these building blocks, the better you are in doing trig identity problems. So please memorize these. You saw where they come from. Now we're going to use these, so please memorize these. In example 1, it says, use the values that are given to find all 6 trig function values. Well, if we know that secant of theta is square root of 2, we know it's reciprocal. Secant is cosine is 1 over secant. So we know that this is the value for cosine. Let's rationalize that. Times root 2 over root 2 gives us root 2 over 2. There's our cosine value. We know secant and cosine. And we also know that sine of theta is negative root 2 over 2. If that's the case, we know cosecant is 1 over the sine, which means that this is, keep, change, flip, negative 2 over root 2, which we can rationalize to make it negative 2 times root 2 over 2, cancel, gives us negative root 2. So we've got we've got cosecant, we've got sine, we've got cosine, and we've got secant. Well, that leaves us with tangent and cotangent. Tangent theta is sine negative root 2 over 2 over cosine, which is root 2 over 2. You can see that that's going to simplify to 1. Negative 1, actually. Because we have negative over the same thing. It'll give us negative 1. And that cotangent of theta is the reciprocal of tangent. It's 1 over the tangent. And we know tangent is negative 1. Also gives us negative 1. So using just reciprocal identities, we can find secant is root 2. Cosine is root 2 over 2. Sine is negative root 2 over 2. Cosecant is negative root 2. Tangent is negative 1. And cotangent is negative 1 as well. We could do the same problem using Pythagorean identities. Given the same problem, given secant is root 2 and sine is negative root 2 over 2, I can use sine squared theta plus cosine squared theta equals 1. Well, what is sine theta? It's negative root 2 over 2. Squared plus cosine squared theta equals 1. The rest is just algebra. Square that, you get 2 over 4. Subtract 2 over 4 from both sides, we get 1/2. Square root both sides. Square root of 1 over square root of 2 is 1 over square root of 2. Rationalize that and we get root 2 over 2, which is exactly what we got when we used our reciprocal identities. Similarly, here's another Pythagorean identity. Tangent squared theta plus 1 equals secant squared theta. We know secant theta is root 2. So substitute in there, square it, gives us 2. Subtract 1 from both sides, take the square root. Tangent theta equals 1, which is what we got before. Actually, let's check that last problem. Look in the given problem, secant is positive. Secant follows x. So secant is positive in first quadrant and fourth quadrant. Sine is negative. Sine is negative in fourth quadrant and third quadrant. We have the double check in our fourth quadrant. So our angle must be down here somewhere. Well, what about cosine in that angle? Cosine is positive. So when we take the square root, we're doing plus or minus. I'm only keeping the positive root because in the fourth quadrant, cosine is positive. Tangent is negative in this quadrant. Tangent's positive here and here. Tangent's negative in the fourth quadrant, so that's why I'm keeping the negative root when I take the plus or minus root. In example 2, we're asked to simplify the expression to one term. One good technique we can use to that is to write everything in terms of sine and cosine. So we keep this in terms of cosine because it's already there, but tangent is sine x over cosine x, minus secant is 1 over cosine x, plus, this is already in terms of sine and cosine, so we keep it, and this is 1 over sine x. If you write everything in terms of sine and cosine, we can get a lot of cancellations. Anytime I have two denominators that are the same, I'm going to try to combine fractions. Cosine x times sine x minus 1 over the common denominator of cosine x, plus, well, look what happens here. These signs cancel and we're left with plus 1. When we multiply this by this, the denominators also cancel because we can cancel across this multiplication. And we're left with sine x minus 1 plus 1. The plus 1 comes from there. Well, minus 1 plus 1 goes to 0 and we're left with sine x. So we've accomplished the mission of writing the expression in one term. There it is, sine x. We're going to see this technique again. We're going to simplify the expression to one term in example 3. And our technique will be to write each and every term in terms of sine x and cosine x. So secant x is 1 over cosine x, and cosecant x is 1 over sine x. I'm going to keep, change division and multiplication, and take the reciprocal of that. Keep, change, flip gives us 1 over cosine x, keep the numerator, change division to multiplication, and we write this as sine x over, this will be over 1. Now, numerator times numerator, denominator times denominator gives us sine x times 1 is sine x, cosine x times 1 is cosine x, and of course that's equal to tangent x, and there is our answer written as one term. Of course, if we're asked to simplify to one term in example 4, we could use our technique of writing this as sine over cosine plus 1 over cosine, sine over cosine minus 1 over cosine. But before we get there, let's see what else we could do. Let's FOIL this. First times first is tangent squared x. Inner times inner is plus secant x tangent x. Outer times outer is minus secant x tangent x. And last times last is minus secant squared x. Notice secant x tangent x minus secant x tangent x. If they've been good little secant x and tangent x, they go off to number heaven. And we're left with tangent squared x minus secant squared x. Maybe we're stuck because it says simplify to one term. But we do know the Pythagorean identity. I'll change colors and go aside. We know that tangent squared x plus 1 equals secant squared x. This is a Pythagorean identity I asked you to know. That means anytime we see secant squared x, we can substitute in this. So our problem becomes tangent squared x minus, well, we're going to substitute for secant squared x. Secant squared x is tangent squared x plus 1. When we distribute and distribute, we get tangent squared x minus tangent squared x minus 1. These cancel and we're left with minus 1. We have simplified it.